these other containers, what I have is liquid nitrogen. Nitrogen is the main constituent of the air. That means that this is essentially liquid air. It is so cold that compared to it, this tabletop is like a red-hot stove. What would happen if you poured cold water onto a red-hot stove? It would boil. And you know, the reaction of the people in the front row is one of the things that I see all the time with people of your age. When I do this kind of demonstration in an elementary school, every one of those kids is on their hands and knees on the floor trying to see what is this wonderful stuff. And somehow or other, that natural curiosity that those elementary school kids have gets squeezed out of them by our educational system. What a shame that is. I invite you to be more like those elementary school kids and keep that natural curiosity about all the wonderful things that are going on in the world. So, we've got this really cool stuff, and we want to cool down our gas. Now here I have a traditional container for hot gas. Or, you know, I'm from the Washington area, we call it hot air. So what I'm going to do is take the hot gas and put it into this container of liquid nitrogen to make the atoms and molecules move more slowly so that they'll be easier to measure. That's the whole point. Easier to measure, we'll be able to make better clocks if we can measure the atoms and molecules better. Okay, so while that's cooling down, let's, here is what we call a dewar. It's really a thermostat, okay? It's been sitting out at room temperature all day, and that means that compared to the liquid nitrogen, this thing is burning hot. Imagine that you took a bucket and heated it up in a fire until it was glowing red, and then took some cold water and poured it into the bucket. It would boil over, and that's what's happening here. Now that flask is Pyrex, right? Okay, I'm sorry. Okay, so it's boiling like mad because the inside of that dewar is so hot compared to the liquid nitrogen that it's just boiling over. So while it's boiling and cooling down the inside of the dewar, let's cool down some more gas. So we got nice University of Oregon balloons here, school colors. So we're gonna stuff this in here.
Oh, தெரியல டேய் என்னவோ பண்றாரு.
Okay, beautiful, beautiful. Cool down those atoms. Now, we look in here and we see that the boiling has subsided, so that means that the inside of the dewar is cold. A lot of it boiled off, so I'm just going to top it up a little bit here. Now, nice fresh flour. Sitting at a room temperature all day. Compared to liquid nitrogen, it's red hot. Imagine what would happen if you took a fireplace poker, heated it up in the fireplace until it was glowing red, and then took it out and plunged it into a bucket of cold water. It would boil over. And that's what's going on here. So I can look in there and I can see the liquid nitrogen is boiling away because the flour is so hot compared to the liquid nitrogen that it's boiling. So while it's boiling away and cooling down the flour, let's cool down some more gas. Because remember, the whole point is we want to cool down the atoms and molecules so that they're moving more slowly. What? So that they're moving more slowly so that they can so that we can measure them better. Okay. Now, let's go over here. The boiling has subsided. That means that the temperature of the flour is now down to the temperature of the liquid nitrogen. It is so cold that when I take it out of the liquid nitrogen, I can crush it like it was made out of glass. This stuff is really, really cold. And if you've got something that cold, well then... to cool down your atoms and molecules so that they're not moving so fast, so that you can measure them better. Yeah, it's just maybe a little bit too big, but I'll just have to push harder. And I think maybe I'm losing a little bit of liquid nitrogen here. Just fill this up a little bit more. Okay, good. Okay, so what else can I do to show you how incredibly cold this stuff is? Here is a nice stretchy rubber band. I'm going to take this rubber band and I'm going to dunk it into this container of liquid nitrogen. Now it's making the liquid nitrogen boil because that's what everything does when you put it in the liquid nitrogen because it's so hot compared to the liquid nitrogen. When I take it out, I snap it like it was a dry twig. But all I have to do is warm it up in my hands a little bit. And it's nice, stretchy. Nice, bouncy rubber.
Racket ball.
இந்த பால் இதுதான் நான்
Now what I'm going to do is I'm going to
இந்த
ask
டெமோ நான்
you
பார்த்துருக்கேன் நிறைய இடத்துல
move up
பயங்கரமாக
so just for a little while. Okay, but I just want you to see how nice and bouncy this rubber ball is. And now I'm going to put it into the liquid nitrogen. Now let's talk about how cold this stuff is. I mean, this is incredibly cold. Unless you have worked in a low temperature physics laboratory, this is probably the coldest stuff you've ever seen. How cold is it? Well, in order to understand how cold it is, we have to think about how physicists like to measure temperatures. Now, normally when we talk about temperatures, like environmental temperatures, we're using the Fahrenheit scale or the Celsius scale. You know, on the Celsius scale, water freezes at 0, Fahrenheit water freezes at 32. And at least where I come from, it's not that unusual for the temperatures to go below 0 Fahrenheit. Even below 0 Fahrenheit, we sometimes get in Washington. Below 0 Celsius happens in most places that are not tropical, right? A racquetball. Remember how nice and bouncy that racquetball was? It breaks like it was made out of porcelain. This stuff is incredibly cold. And, you know, if you want to cool something down, it seems like this would be a really good place to start, which is why we put the balloons into the liquid nitrogen to slow down the motion of the atoms. But the more astute among you noticed there was something a little bit funny going on here. Because the volume of the balloons that went into here was far greater than the volume of this bucket. In fact, these balloons have turned into pancakes. They have not kept their original velocity. They are now like frisbees. Now, how many green and yellow balloons did I put in? Four. How many blue ones did I put in? How many tie-dye ones did I put in? White ones. You see, this was filled up with balloons before we started. So these, but the air did not go out of these balloons. The air in these balloons condensed. And you see, all you have to do is let them warm up again, and these balloons are reinflated. So what was going on? Yeah.
God.
what was
Super
going
raw.
on is